Okay, so today I'm going to cover two topics that are a bit tricky, so I go slowly. You're going to see this many times, but that's the first time that I'm going to present. It always takes us some time so people can digest the topic. So today I'm going to just introduce what's a Markov equivalence class, or what are Markov equivalent models, and the definition of the definition of Markov equivalence class, and also I'm going to give some, not only the definition, but some examples with this separation. So Markov equivalence class is going to be a topic that's going to be used for many lectures starting from today. And this separation is a fundamental tool, so you need to understand this really well. I would say that these two topics are fundamental for 9% of everything that we're going to say in these lectures, in this class. So just stop me at any time if you don't understand something. So from the previous lectures, we saw that there are two different roads, right? So there's the observational road in the left side, where we basically is the environment as it is, so it's the nature, and everything that we collect from this environment is going to have loss of information, right? So we are going to lose some information, for example, if we just collect data. So this is going to be observational data. And the observational distribution that's induced by this observational model also doesn't capture completely the structure causal model, or the SCM, that's the model that generated the data. And even the DAG is just some structural description of the model, so you don't have information about the functions themselves. So the step of getting information from this nature, that is loss of information. And we are usually under this scenario where you have available either only data, or in some good scenarios you have some description of the structure, but that's what you have in the end. You usually don't have the completely specified SCM. And this is the observational world. We say that's the passive reality. When we apply an intervention, for example, a do x equals to small x, or we are changing the value of the variable x, we are also changing the entire model. So the model, or the reality, is now described by a model that's kind of similar, but the difference is here, where we, instead of having the variable x, we set as small x. And the objects that are induced by this model are also different. So we can observe a few differences here. So the data, so suppose that we actually performed an intervention in the world. So the data that comes from there is the probability of V, or the data can be used to estimate the probability of all the set of variables that you observed given this specific intervention, x equals 3 small x. And the diagram that corresponds to this graph also is going to have a difference in the functions that determine the variable x, because the x doesn't take now the values of ux and uxy in this case. So no edge that was into x are going to appear in this interventional causal diagram. So we have a difference in these two roads. And the special thing in causality, or the special challenge that we have in causality, is where we have the objects induced by the observational world, and we want to infer, without having an intervention, we want to infer something related to this role in the right side. And why this is hard? So today we are going to understand why this is hard. Okay? So that's just an animation that I prepared here, but basically it's the same story, right? So we have two different realities, the observational one on the top now, and the interventional on the bottom, and both induced diagrams. So we have a diagram there that has latent variables inducing influencing both x and y. So those variables are called confounders, right? Latent confounders. I'm not describing them, but they are usually this uxy here. And the graph is called G. And we are going to have this notation. You don't really need to know this now, but you are going to see later that every time that I have this x with a line on top of it is because I'm removing edges into the variable x. So no edge that was into x appears here. So since there's only one, I remove completely this, and this is called interventional graph. The data that we have available is the observational data usually, right? So if we just collect data from a hospital, for example, you don't perform an intervention, just collect the data. This is in the top here. And in machine learning, what we do is try to get, and we actually didn't perform intervention, so we have no data here, right? In machine learning, we usually do this. We get the data, we run deep neural network, we fit a deep neural network or any of your favorite machine learning algorithm, and what we can predict is this p hat, right? So we don't have the real probability, but we can estimate it from data. And deep neural networks are in universal approximators, right? We all know this, but they are universal approximators of the observational distribution, and that's really important to know because what we want is a different thing, is the probability after performing one intervention where we don't have access to this. We haven't performed the intervention yet. So the challenge is how can you move from the seeing world or the observational world, if you remember of the Pearl's causal hierarchy, how can we move from the first rung of the ladder to the second rung or the interventional layer of the causal hierarchy? Right, so this is the biggest challenge. And as I said, why this is hard? So when you have observational data, the signature that we have in the data is conditional independencies. So basically what you can do from data, observational data, is estimate correlations. And these correlations can be conditional on something or not. So we call these dependencies, these associations, statistical associations as dependencies and independencies. And they can be conditional dependencies or condition dependencies. But this is all that you can get from data. The only thing. So you can get the statistical tests, get answers about if the variables are associated or not. And this is sufficient to estimate this probability of y given x, observational distribution. This is what deep learning do. They just check associations, statistical associations, and can actually perform, be very accurate at estimating this quantity, probability of y given x, for example. However, that is an issue. The same observational distribution, then it can, so for example, suppose we have this x and y. X and y, two variables. Suppose that x and y are correlated. You observe that they are correlated. A model that could generate x and y correlated could be described by many. There could be many models actually that could generate the same relationship between x and y, the same numbers even. So it could be, for example, a model that has this G1, this graph G1 as the structure description of it. So we have that x is actually argument of the function of y. We have some latent confounding, and this generates data where x and y are correlated. You can also have this and generate the same data. I can actually give you a model. You can try at home to get like one different parameterization of x and y and get the same correlation between x and y, the same observed correlation. So for example, 0.8 Pearson correlation. So you don't really know why there is this 0.8. Could be because x was a cause of y, but could be also that y was a cause of x with different confounders and so on. Could be just this, just confounder. There's no cause at all. None is causing the other. So could be this. Could be just x causing y with no confounders. Could be y causing x with no confounders. So when you actually see x correlated to y, you don't really know what's the model. If you don't tell me if it's x first and then y later, or if you don't tell me that there is no confounder, you cannot decide between those. All of those are correct according, or not correct, but they are all probable to be the true one. They could be they could be describing the true generating model that generated this correlation between X and Y that you observed. And it's worse because you saw how causal diagrams are defined. And there are many models actually that generates the same structure, because since I can change the functions, I can change the probabilities, I can change everything. And the only thing that matters when I create the causal diagram is just the order, or who is argument of the order. There are many models that could actually be generating this graph. And I put in red there because suppose that that's the true one. And then, doesn't matter, could be this one, the true one there. But all those models could be a perfect fit, I would say, to that data where probability of Y given X. So in a different story, suppose that you are feeding a structural equation model, so people from statistics likes this, and then you draw the functions where Y is a function of X plus an arrow. You can even like put other variables there to explain some possible confounding, and you are going to have a very high index, like a goodness of fit, like a R2 or something like this. But this doesn't matter. This doesn't mean that the model that had a goodness of fit actually is the true model. Because any model that you could write here would have a perfect fit if it's, I mean, there's always a statistical error, but if you get perfectly here a model and you feed the data without no noise or whatever, you would have like a perfect fit for all of those models because they are all equivalent in the sense of generating a correlation or a statistical association between X and Y. So that's why, there is this as well. So some people can say, but I know I am in that case where I observed all the variables. So we call this causal sufficiency or Markov parameterization. So we are under a Markovian system. We are going to define this later. But even in this scenario where you observed all the possible variables that could explain our phenomenon, you also are not in the case that you can decide if it's X causing Y or Y causing X. You get rid of the dashed line because those are the latent confounders. But if you have no latent variable at all, so you observed everything, so there's no latent confounder, you are still in the case where many models are equivalent. So when you feed you can feed like multiple neural networks. The neural network that's going to be the parameterization of this neural network in the end is not going to correspond to the true data generating model. It's going to be a good approximator of the observational distribution. So you can use this to do predictions, because I can do predictions just with the observational distribution. But you can never make the mistake of believing that this model is useful to do decision making. Because for decision making, you need the true data generating model. So for example, if you train a model with machine learning, and then we start like, what would happen now if I change one feature to another? That's sensitive analysis, right? So if you change, what would be the outcome? Is this because in the reality it's going to have the same outcome? No. Because you're using a different model. You could be using the true one, but what's the chance? You have multiple models. But okay, if you are not in the case with the true one, you're going to just be lying to yourself. Everything that we're going to see as outcome of this model is not necessarily what's going to happen in reality. You cannot use never this. You can just use this for prediction. It's tricky. So when you publish a paper and you say, I could generate I could feed this deep neural network to predict heart disease very well. Perfectly. You can, go to a hospital and use this to help diagnosing heart diseases. But you can never use this model to understand why people have heart disease. unless you know that this is the true generating model, unless you try to investigate this in a causal perspective. You understand? Because just from data, you will never be able to get the true generating model. So this is very, very important to know why the challenge is there, because just from data, it's impossible to actually decide among all these models. So today I'm going to give you some definitions about the first layer of the pro-causal hierarchy, which are the observational layer. So I'm going to talk a little bit more about the signatures that are inside of the observational distribution. So usually are in terms of condition independences. And this is going also to be described as an object. Maybe some of you already heard about Bayesian networks. So Bayesian networks are encoders of condition independences. And we are going to see that this is a very useful object. However, it's not a causal diagram. It's just an encoder of condition independence. We are going to see this. Questions before? No? Okay, so that's just a formal definition of what's L1 valuation or observing. So basically for an SCM, so that's how we defined SCM last time. So it's just a tuple, remember? So we have a set of variables V, observed, U, unobserved, a set of functions and the probabilities of U. And this model induce or define a distribution, and this is a probability distribution, which is going to be called observational distribution. And it's kind of defined in this way, right? So for this is the usual definition of probability, right? So I hope I'm not the notation is a bit different, but I hope I'm not telling you anything new. So it's just the probability. Let's just parse here the probability that's induced by a model M, and let's get a set of variables Y in this case, and the variable, the probability of the joint, right? So the joint probability of Y is going to be the sum of the probability of all the U's variables. So in the exercise sheet, maybe you notice this. You can always convert all the observed variables into U variables. So you can always just get the U's variable. So it's just the sum of all the probabilities of U's. That's why this SCM only needs the probabilities of the U's. And as the sum for all U, such that the potential response, or the U that would be have the value of U, the variable of the variable U, that after having this specific set of U's is exactly the U that we're talking about, right? So you just compute the probability of that specific U's that are turning into Y equals to small y. And right, so YU is just the solution after evaluating Y with the U's, and the probability P U equals to U is just a probability mass. So that's just the usual definition of distributions, right? So of probability distribution. And there's nothing new here. So basically you just need to compute, that's the difference here. What would be the Y after evaluating in these equations in the structure causal model, evaluating these equations with the U equals to 1, and then you get the probability. And this distribution, which is induced by this SCM, can also be represented by a graph. So the graph has a name here, so it's just a graph, nodes and vertices and edges, but they have a different name just because it's explaining the type of graph. So right now it's just a graph, right? So the graph, it's called directed acyclic graph. If it's a graph which is acyclic, so there's no cycle, and the edges are all directed. And this is the short of this is DEG. We call it DEG. Maybe you have heard about. But this is a graph. There's nothing more here, right? Sometimes when we have latent confounding, we can use a different type of graph, which is going to be called acyclic directed mixed graph, because it's not only acyclic and directed, but it's mixed because they're directed edges and is dashed by directed edges. That's why it's mixed. So it's just a name, but it's just a graph. To actually give a probability or a probabilistic meaning for a graph, we need something more. We need to say what's going on with these edges and nodes. So the nodes are going to be random variables, and the edges are going to define something that we're going to see maybe in 2 slides. But before this, so this is, for example, a DAG. Like I want to start with the DAG, so no latent confounder, because that's the way that the field started as well. And it's going to be easier to understand the concepts. Then we are going to extend the notion to allow the existence of latent confounding, and then we are going to extend also the notion of Bayesian networks with this. So this is the DAG. So you see here there are nodes and edges. So the first thing to note here is that we are going to use this graph to represent probability distributions, right? So this actually encodes a joint probability distribution where the random variables are represented as nodes in the graph, and the edges are going to be the following. So they are going to have this type of kinship notation. So we're going to use family notation to describe the relationship between the variables, and it's easy. So every time that there is an edge, a direct edge between a variable and another, the one that's pointing to another is the parent and the other is the child. So for example, X and Y are the parents of Z there. And we call this PA. And then the Z is the child of Y. It's also child of X, but we use this notation CH. There's also descendants. So descendant is like in families. Everything that, including a child, is a descendant. So in this case, the Z and the W are descendants of X and Y. So I just gave an example here. W is descendant of X, right? Because W is that is a directed path that goes from X to W. So X is a parent of Z, and Z is a parent of W. So instead of saying grandparent, we are going to say just ancestor or descendants, right? So X is an ancestor, maybe that's the next. So I use the other example, the other side, Y is ancestor of W, right? But X is also ancestor of W. X and Y are ancestors of Z, right? So everything that follows the usual intuition for families works here. We have also the notion of non-descendant. It's maybe a bit tricky here, but Y is a non-descendant of Z, is also a non-descendant of X, is also a non-descendant of W. It's just because it's not descendant. So if there's no directed path from from Y to W, from W to Y to make Y descendant of W, then Y is a non-descendant. But you have to observe like other types of paths, like X is also a non-descendant, right? And that's the notation, and desk. That's a note that sometimes it's important to know because I try to always clarify if I'm using this case or not, but in many cases, parents, ancestors, children's, descendants, they include itself as part of the set. So I am, if I'm a node, I am my parent. I am also my child. I'm also my descendant. It's really weird, but that's just to make notation easier. So many times you are going to see,
If W is a descendant of X, Y, and Z, that means W's function is dependent on X, Y, and Z, right?
Descendants, no. Parents, a function only is direct association. So W is a function of Z.
Oh.
Z is a function of Y.
Yeah, okay.
Later, you're going to see something called projection. So if you remove the Z from the graph here, you would have to complete W as a function of Y, W as a function of X, because you have to preserve the relationships.
Mm-hmm. Is W a descendant of Z?
Yes.
That also works. Okay.
Yes. Imagine like as families, but the only weird thing is this note here. But it's just mathematical reasons. But I will always try to clarify. Many papers don't do this, so sometimes you start reading it and, oh, okay, That's the weird definition, and then you have to go back and try to understand. I will try to clarify if it is the case or not of using descendants and children as part of myself. So that's just an example, right? So X could be the child of X, right? So X belongs to the set of children of X. Ancestors of W includes the W, right? That is this, maybe it's not so direct to see, but the parents of a set is the parents of each element of the set, is the union. So for example, parents of Z and W are the parents of Z union with the parents of W, right? Ancestors of W are all, it's a set of, there's only one here, so all the ancestors of W. So here, parents of Z and W includes Z and W, see? But also, that's the way that you do it. So this, if the argument is a set, you just take the union. Okay, questions related to this? Okay.
So parent has to be the direct line before it,
Yes.
but descendants, what is it?
You can have
The
child
ancestors,
as the direct. So W is a child of Z,
Yeah.
but also a descendant of Z.
Okay.
W is a descendant of Y,
Yeah.
but it's not a child of Y.
Okay. So child and parents are subsets of descendants.
Yes.
Okay, I got it.
Okay. Okay, so that is this condition that I wanted to call call your attention, because it's is one of the conditions necessary to make the connection between a graph, which is a mathematical object without no meaning, with probability distribution. So we are going to connect and make the object as a probabilistic model, right? So it's not for free that a graph is a probabilistic model. We have to call or to use some assumption or condition for it. And this is called Markov condition. So a Markov condition says the following, the definition. So a probability distribution P is going to satisfy the Markov condition for a DAG. So I'm using, again, remembering, so I'm in the Markovian case. Let's forget about latent confounders, right? So we are in this case where there's only directed edges in the graph, so it's a DAG. So it's going to satisfy the Markov condition with respect to a DAG if for every variable V, so the observed variables, the ones that are nodes in the graph, it's holds that Vi is independent. So this is a statistical condition, it's independent of all the non-descendants in the graph given the parents. If this is true, we are going to see an example, then we actually can use this graph to describe the joint probability of the set of variables V, and then we can even simplify how you factorize the probability distribution. So the first line you learn, probably you even applied in this exercise sheet, is just the chain rule. So it holds for whatever order that you pick for the set of variables, the V, in V. So you can just choose any order here. But you can only simplify from the first line to the second line if the variables that you remove are independent of the parents. So here I'm using this condition because a variable Vi is going to be independent of everything that comes before it, right? Because I choose a topological order here, and everything that's before it is a non-descendant. So Vi is going to be independent of everything that's not parent given the parent, right? Everything that came before is not a parent is a non-descendant, right? Descendants comes after. So I'm using from this line to this line this condition, and I'm simplifying. So you can say that using this condition, I am showing the most simplified way of factorizing the joint probability, the probability distribution PV. So I'm using here. So let's see an example. Let's see if I I just wanted to say that right now we are not using causal semantics, right? So this is just a graph. My only goal here is to connect this graph to be an encoder of a joint probability distribution, a joint observational distribution. No causality here. So suppose that I have this graph, and then I can factorize using any order that I choose. So I just chose this one because I wanted. So I picked W, and then everything that's before W. So actually the order that I chose was W, Z, X, Y, and A. I chose an order. I can choose any order. But everything that's coming after the bar here can be simplified. And I chose this particular order because I wanted to follow this graph. So this would work for any graph. But if I want to follow this graph, I have to follow the order that's induced by this graph. And then I can use this order, this property following also the graph. So in this case, W is going to be independent of everything else just given Z, because Z is the only parent. So I can simplify this. I don't know if I put this step by step. Yes. So W is independent of everything else, which is X, Y, A, given the parent, which is Z. The other one is Z, and if you go to the graph, you see that the only parents are X and Y. And the variables that are before are just the A. So Z are going to be independent of A given X and Y. That's what I'm going to write here. The next one, can someone tell me what's going on?
X is independent of Y because Y is not a parent.
That's good.
So X is only dependent on A.
Yes, exactly. So Y is a non-descendant of X, and X is going to be independent of this non-descendant given its parent, which is A. And then the others are easy, like I have no simplification. So I can simplify. So this is equivalent to this one. And this factorization is a factorization according to the parents, we call it. Factorization according to the parent. And only works because I'm saying to you, if I give you this graph and I say this probability distribution satisfies the Markov condition to this graph, how can I simplify them? Right? So I have to tell you, this satisfies the Markov condition. So P is said to satisfy the Markov condition relative to a graph. If I tell you if it's happening, then you can get the order of this graph, because you can choose any graph, any order. So I can choose the order of the graph and then apply the condition of the V being independent of its non-descendants given its parents. Okay?
Why do we have Px given y and a, but then for Py there's no x in the a? Like,
where are you?
Py given x and a.
Py given
in the PV.
Here?
Yeah, so in the green box we have Px given y and a, but then right next to it we have Py given only a.
I'm just copying what's left because I couldn't simplify this.
It's a chain rule. You're applying the chain rule.
Oh, it's a chain.
After,
Okay,
afterward,
I see.
Like
Right.
that's how the initial.
Yeah, so this one works for any topological order. I just decided to pick the one from the graph, right? So I could write this a chain rule for any order. I'm just writing for the order of the graph.
I got confused.
But following the graph, given that the Markov condition holds, I can do this, right? Okay, so now we have the idea of connect. So we connected graphs with probability. And there is this term that's called independence map. So we can, let's define. So if for a distribution and for any sets x, y, z in V, it holds that what's implied by the graph, it's actually hold in the distribution, then G is going to be called IMAP or independence map. It's just a name of it. So in this case, G is IMAP of the probability. So why this is true, I'm just going to tell you. So from this graph, there's no independence holding because all the variables are connected. So that is, you can even apply, but you can see like B is independent of its non-descendants given the parents, but the parents is both. And A are so if you choose for, you can try to write all the factorizations for any topological order for this graph, and you're never going to simplify it. You can try at home, but this is because this graph is not implying any condition independence. So there's no separation between any variable here because you have all the edges. And because of this, the graph is called the IMAP, because this is holding, right? So there is no implication. So because it's no implication, there's no way to violate the no implication. So since there's no independence in between the variables A, B, and C, this is true for any probability. There's zero implication, so I can never make this wrong, right? And that's why G is an IMAP. So just telling you that the if for every separation in the graph implies real independences in the distribution doesn't tell you much because of this. I can give you a complete graph, and this is going to be true all the time because there's nothing being implied by this graph, so I can never make this wrong. So always a complete graph is an IMAP. So I want something more. That's what's written here. A complete graph trivially satisfies this condition of being an independence map because I'm representing no independence. So what we need is minimal IMAP. So to define Bayesian networks, we need something more. So a Bayesian network is actually we need to see what's a minimal or a perfect IMAP. So a Bayesian network is going to be a minimal or a perfect IMAP. This means that the implication from the graph has to be minimal. So let's read it. So G is going to be an IMAP of P if none of its edges can be removed without seizing its IMAP property. So I want to be the most sparse graph as possible without implying false independences. So I want exactly this. I cannot remove any other edge without this still continue being an IMAP, right? So that's the minimal property that we're looking for. So a Bayesian network is going to be this. So it's not only a directed graph, but it has to be an IMAP, a minimal IMAP. So not only it works that every implication from the graph it's true in the probability distribution, but also that I cannot remove any edge without seizing the property of being an IMAP. So it has to be the most sparse graph as possible.
Can you show a quick example of what isn't an IMAP?
Right now. So suppose that I have this probability with just one independency being true. A is independent of C. Okay? Then I ask, is this what? IMAP, a Bayesian network? First of all, is an IMAP? It is, because it's complete and there's no independence implied here. So it's true. But A is independent of C. Do you think A is independent of C here? So A and C are connected directly. So there is no way to make A and C independent. So you have the connection parents there, right there. So this is IMAP, but it's not a Bayesian network. This is the same thing, right? So it's again a complete graph. So it's again an IMAP. So it's just a different complete graph. So I changed the orientation of A and B, but it's still an IMAP. So it's still true that this represents the PV. So if I ask, is this representing PV? It is. I can write the chain rule and it's going to be true. I just cannot simplify it. So it is an IMAP. It's completely representing the independencies that I can actually have, which are none, but it's not the most sparse graph as possible, right? What about this? Maybe you can start writing the chain rule. So you're going to see that, let's see if I can write here. The point is, I could simplify using the idea of every variable being dependent of its non-descendants given the parents, and that graph it's showing me all the condition dependence that exists in my probability distribution, which I'm saying that's the only one there. So it's the most sparse possible. So if I removed any edge, let's suppose I remove A and B, the edge between A and B, then it's seizing the property of showing only the independencies that exist in my distribution, because now I'm showing that A and B are independent, which is not true. So that graph actually is the minimal one, and it's an IMAP and a minimal one, so it's a Bayesian network. So yeah, exactly. So we will see a tool to read this condition dependencies really easy. This is the separation tool. That's why I said I changed the order of the slides, because I think it's more interesting to present before the disseparation, because you can actually detect this through these factorizations. So, and that's the way to see why it's important to connect just the concept of graphs with probability distribution. So the goal here is to have a graphical representation of the joint probability distribution, but not any representation. I want the one that generates the most simplified factorization. So that's why I need the minimal IMAP. So this is what's called Bayesian network. Bayesian network is a graph that implies this factorization over the parents. That's the definition. So if you're going to see the definition out there, they're not maybe going to show you the definition using minimal IMAP. Maybe they're going to say just that implies this factorization of the parents, of variables being dependent of the non-descendants given the parents. But I think it's clear to see from this point of view, like you want a graphical representation of the joint probability distribution, where you can use this property that's a consequence to actually represent the condition dependencies. Okay, so it actually is an IMAP, it's an independence map, it's a representation of condition dependencies, and that's all. So Bayesian networks is only that, is representing only condition dependence. There's no causality here, right? So that's why we have this issue. So if we have now a different independence, so we in our example it was A independent of C. Now I'm saying something different. So I have three variables, X, Y, and Z. And I'm saying that the only independence is that X is independent of Y given Z. Okay? So if I started factorizing, so I pick this one, for example, then I can apply Z, remove there from, I can actually remove the X, because X is independent of Y given Z, right? I'm just telling you this, right? Then I have this. I could have then this Bayesian network representing, because it's exactly this. So the Z has the X as the parent, as is showing here. X has no parent, and the Y has Z as a parent. Okay? Now, if I pick another order for my variable, for my chain rule, I started with X now. X, then Y, and then Z. And the X is independent of Y given Z. I'm applying the same thing again. And I generated another one now, where gives me this graph, where X has Z as the parent. So X has Z as the parent. Z has Y as the parent. And Y has no parent. Okay? I can give you another one now. Y, then X, then Z. And again, Y and X, I can remove the X because X and Y are independent given Z. And then I have this. And this gives me this network where y is the has z as the parent, x has z as a parent, right? X has z as a parent, and z has no parent. So 3 different graphs are Bayesian networks or minimal IMAPs for this independence x independent of y given z. They all work. They are all perfect or minimal IMAPs for representing this set of condition dependencies, which is just x independent of y given z. Okay.
For the second equation, how does the two right probabilities, they like swap? So for the second equation, we have on the right side p y given z and p of z, and then in the next line it becomes
it's
p
a
z
type.
given y.
That's a typo. I guess I should have z y here and y because exactly what I wanted here.
Okay.
So the order should be x, then z, then y. Thanks for I fix later. Right, but it's correct. So 3 different factorizations giving me 3 different graphs. So if I give you x independent of y given z, what's the best graph? I give you this data, and x and y are independent of z, okay? And then I ask you, which graph represents my data better?
Which graph represents your data the best?
Yeah.
I think they all do it equally.
Yes, exactly. So they are all good. So if I give you an algorithm that learns what's the best graph to represent my data, what do you think the algorithm should do?
It should find any graph that represents your data.
All the graphs, not
It should
any.
find all the
They
graphs.
should all the graphs.
Oh. Okay.
So later we are going to see that the algorithms that try to recover the graph learns a representation of the whole class, because this is what you have in the end. If you have invariances across these methods, this is what you want to learn. So this is where it comes this next example. So suppose that I give you now x independent of y, and then I try factorization. So I try this one where z, then x, then y. And I said that's just this, x independent of y. So this term can be simplified to this one. And then when I write the same guy here, of the Monthal problem, why it's so special? Why this graph is appearing all the time? This guy with the z being a collider. I'm talking about collider a lot here. Why?
Maybe because the independence assumption in there is stronger than in the example before, because there we have like only this conditional independence, and here we have an actual independence between the two variables x and y.
No. So I'm saying here, so in this case, I have also one independence. All the others are dependencies, right? So everything that I'm not writing is because they are dependent. X and y also, it's the only one. So both can be very strong.
Maybe the collider appears often because like this normal independence, every time you have like a normal independence, the collider appears.
Every time keep what?
You have like an independence of this sort, a collider appears.
Yeah, kind of this, but the point is that we are in this scenario where there's no latent confounder, right? So don't forget about this. The most special thing about it is that it is the only one in its class. So it's the only case that if I only observe x and y being independent, all the other possibilities are dependent. So it includes x dependent of y given z, x and z independent. So all other combination are dependencies, right? But if you give me a data set where X and Y are independent and everything else are dependent, even conditional to other variables, that's the only graph that represents it. So that is uniqueness in this problem. So you have actually identifiability. So in this case, so I think I mentioned this already. So in the first case there, I have 3 graphs that are considered equivalent. So they are called Markov equivalent because they all imply the same set of condition dependence. So we have this definition of Markov equivalence. So models that imply the same set of condition dependencies, they are considered Markov equivalent. So for the case of X and Y being dependent given Z, I have 3 equivalent models. But for the second one, I have only 1. So these 3 are Markov equivalent, but in this case, I have identifiability. There's only 1 graph. Is one of the cases under the assumption there's no latent confounder. It's the only formation that I can for sure tell that that's the graph. So of course I cannot say what's the function that generates the Z, but I know that Z depends, it's a function that depends on X and Y. And that's the correct order. It's never the case where Z is a descendant, sorry, it's a non-descendant of X and Y. It's always even a child, right? So we have this collider case, and the collider is identifiable.
Like, as a question for why it is important that it's identifiable, because I thought we always have the distribution and then we get the Bayesian networks from the distribution. Why do we need to have it identifiable on like the way back?
Because I wanted to learn more about the data generating model.
Okay.
So if so, I started from this. So so the first lecture was about this. So if I said I found that A and B are correlated, can I know something about which comes first?
Okay.
Is A coming first than B? Can I do some decision about it? And I said no, because then I started this lecture saying, why not? Because there are many graphs that could actually explain this. But if you give me a data set where the only independence that holds is this, but everything else is dependent, including X independent of Y given Z. So I'm conditioning on the collider. So that's the case of the collider bias. Remember the example where I condition on the site and then mental disease became correlated to cardiovascular disease. So I had the example where X and Y are dependent given the collider, which is the site. But mental disease was independent of cardiovascular alone. And this information was sufficient to know that if under no latent confounding, that the Z is caused by X and Y. And given this graph, I would know for sure that X and Y shouldn't be analyzed by conditioning on the collider. So knowing the graph gives you more information to know better which type of analysis you should do or which type of associations you are getting out of it.
And sometimes you start with the graph.
If you have the graph, you can do much more. So if you have the graph, you know for sure what are the types of associations you have, right? Because if the graph is already a Bayesian network encoding your condition dependencies, you know already what you have to expect. So you know by looking at the graph, you don't even need data. So the graph tells everything. You know which variable is connected to other, condition to everything else, because this is what this separation is going to tell you. I hope I'll get there. So the graph tells us a lot. So, but the problem is like usually we are in the first layer of the causal hierarchy. There's just data. You don't know what's the graph. But that's a case where you can learn one specific characteristic of the model, which is Z is a collider. Okay? And this is a lot. Okay? So yeah, now it comes the case Bayesians with latent confounders. you need this definition. It's not that complicated, but there is this confounded component. So maybe I should go directly to the example so we can follow. So a set of nodes, a set C. So since we are in the case of latent confounder, we have bidirected edges, right? So we are no longer talking about DEGs. We are now in the acyclic directed mixed graph, right? So there's another object here. It's just a graph, nothing else, but it has mixed types of edges. So this node, it's going to form a confounded component of this graph if every variable in the set C is connected by a path that's made entirely of bidirected edges. So for example, in my case here, I have just, okay, maybe I will ask you, what are the confounded components of this graph? So it's just a set of variables that are connected with bidirected edges. Or bidirect, it's a path of bidirected edges. So it could be longer, right? You.
C and E and B and D?
Yes. Okay. This component has to be also maximal, right? So if we had like a longer path, I have to keep connecting the variables until being maximal, right? And then we can define something that's called extended parents. So as I said, I defined this idea of parents and descendants and things in a graph that there's no bidirected edges. But here, all the other relationships are the same, except by this idea of extended parents. We need something more. So let's just go slowly here. So basically, an extended parent is defined by this PA with a plus, okay? I'm clarifying here that the parents are the sets of they are the parents of the variables plus the variable itself. So we are in this weird notation with parents. I am my own parent. So this PA1 is just to make sure that you understand what are the type of parents I'm talking about, but it's just parents. So for every variable in this component, C component or confounded component, so for every variable that's before some topological order, so there is order here, so we pick a topological order, and for every variable that's before, I take the parents of it, okay? We'll see an example. So, I gave this is the answer. Maybe for the other. Oops. Yeah, for the other, I make the question. So this is the parents, the extended parents of the variable E. Okay. So what I need to do is first get the component, the C component, where E is part of it. So E is part of the C component with C, okay? But I need to get a topological order of this graph. And the topological order of this graph, E, comes after C. So C, then E, right? That is this path here. So that's why E comes after C. So for every variable in the C components, that's what's telling here, I need to get the parents of this variable if the variable is before the variable itself. So, so the variable itself is E. Let's start with it. So who are the parents of E?
D.
I heard more than D. It's just D, right? The only parent. So this here. Then we go to the other variable in the C component, which is before E. It's C. So C is both in the C component and it's before E. So I'm going to take the parents of it. The parents of it, who are the parents of it? A. So A is here. And the variable itself, it's also here. I don't get the parent itself of E. Actually, I get it, but I remove it later, right? So you do this process. I should actually include the E here, but then I remove the E afterwards. Got it? But basically, it's just the parents of every variable in the C component before the variable itself. Okay? Let's get the extended parents of D. Let's start with the D itself. Now, first, what's the C component of D? B and D. And I want the parents of every variable in the C components which are before D. So both B and D. Okay? So parents of D, who are the parents of D? B and C and D. Then later we were going to remove the D. So I write here. So B, D, and C, right? So the parents of D are B and C, but D is also parent of itself. Then we go to B, because B is before D, so we try to get the parents of B. Who are the parents of B? A and B. So B is already here, so we add the A. But then we remove the VI, which is E. Oh, which is D, right? So in the end, it's ABC. This ABC. Okay, so now that you know this, that is this extension of the Markov condition. So before, remember, we started with a DAG.
Sorry, for the previous slide, what about PAB? Because then D is not considered because in topological order, yes, that's
Sorry,
for parents of B.
parents of B is just A.
It's just A because D is not anymore considered because
No.
in topological.
We need the parents. Parents are variables pointing into B.
No, I mean.
But it's also
PA
in the C
plus
component.
B. PA plus B. PA.
The extended parents of B.
Yeah, the extended parents of B.
Ah, okay, yes. Yes, so extended parents, maybe that would be a better example. Yes, so we just get the parents of B because D is after it,
Okay.
but then would be B and A, and then we remove B, so it's just A. Actually, everything that I'm not showing here is because it's exactly the usual parents. Right. So, this was important because I wanted to connect again the case of a graph with a probability distribution. So that was the goal before, and I said that the Markov condition is what allows us to do this with DAGs. So in the case where there are no latent confounders. So actually Bayesian networks, a bit of history here, it started with DAGs. So if you look at the internet, what's the definition of Bayesian networks? I'm sure that you're never going to find this definition because this is kind of in the mind of the current researchers right now, but no one wrote about it. And the definition of Bayesian networks has been always in the case of the no latent confounding. However, we can call a graph, which is the ADMG, so it's just a mathematical object, that has this property. So this was actually written in this reference that I put on the end of this lecture. That's a book chapter written by Elias Barenboim. He wrote about this, but he didn't say that this is extend Bayesian network. He's just calling this as a encoder of the conditional independencies. And the semi-Markov condition is going to do what the Markov condition did to pegs. Oh, sorry, to DAGs. Many names. Don't confound. Sorry. So Markov condition allows DAGs to be Bayesian networks. Semi-Markov conditions are going to allow ADMGs to be Bayesian networks. Okay? And that's the condition. So a distribution is said to be semi-Markov condition. For some reason, people believe that semi helps here. It's the same thing as before. It's a Markov condition. So semi-Markov condition now is relative to a ADMG, okay? If the condition is pretty similar, but now instead of conditioning on the parents, we condition the extended parents, and it's going to work. Simple like this. And then the factorization is also going to work. Remember that the joint probability could be factorized as the probability of every variable given the parents, right? Remember this? Now it's the same. It's the product of the probabilities of the variables given the extended parent. So you just put them plus here, everything works. But you need to know the definition of these extended parents. So in our graph, we know already what are the extended parents. So just to go fast here, we just apply what we did before. So maybe we can, I don't know if you remember, but so the E here, we computed the extended parents of E was D and A and C. D, A, and C. Everything else is independent of E given these extended parents. So just simplified. The D, so we computed also. So it was this, A, B, and C. A, B, and C. For the others, it's just the usual parents, right? So C depends on A, is the only parent, so it's independent of B and F given A. B is independent of F given its parent, which is A. And the others are kind of not possible to simplify. Okay? Questions? So we know now how to connect graphs with probability distributions. Okay? Fun thing is that when we add the latent confounders, so we can do the same thing. So I'm going a bit fast here just so we can finish the lecture. Actually, I go a little bit over again. So a distribution x, y given z, if we start again writing this in terms of the extended parents now, right, so first the chain rule, then we apply the independence as before, and then we construct a graph following now the rule of the extended parents. You could generate the graphs as before, but also many others with adding this bidirected edges. You can do this later. But basically, you can choose a chain rule, apply the chain rule, like using any order. Every time that you could simplify, then you can construct graphs. So for example, for the first one, there are not only one, but there are many, because you see the extended parents of z are still just x. Doesn't change by adding a bidirected edge. So you can actually add bidirected edges without changing the factorization, and it's still representing the same joint distribution. So now that list of graphs that represents x, y, and z, given the fact that I have no latent confounders, now it's much bigger. I have many more, and they are, in the same case, they are Markov equivalent, right? Just the class is bigger now. With the other case that I said that the colliders are special, so x and y are independent, all others are dependent. If I start doing it, I can actually construct many variables now. But it's funny because that is actually an invariance. Although I'm adding many bidirected edges, it's always the case that z is a collider. So let's go back here. You can see here, there's never an edge out of z. It's always an arrowhead in z. So the collider, also in the case of latent confounders, is a special one because it's going to be learnable. He's learnable. The collider is learnable, and we are going to use this when we are going to see algorithms to recover graphs from data. So we would be able to detect that the z is always a known ancestor of x and y. I'm not sure how is actually related, but I'm sure that there is an arrowhead into it. So I learned the arrowhead, and that's nice.
I have a question. In this case, another possible graph would just be the old one without any confounding, right? Is that still possible under that?
It's still possible. I don't know if I didn't put here. There are many here, right?
Oh, okay.
Yeah.
I didn't see the dot.
Yeah, no, the class is huge. Yeah, the other one is still there.
So you said we use this to recover graphs from data.
We can recover pieces of the graph from data. So identifiability of the graph can only happen. There are algorithms that exploit this, but the conditions are like, for example, that is this algorithm that's called Lingan that assumes causal sufficiency, so no latent confounding, assumes linearity, and assumes no Gaussian error terms. All of this. Then you have identifiability. Some people like to do this, but then you have to be sure that your assumptions are true in the end. But that is an algorithm that gives us identifiability under this condition. So there's a line of research of trying to find identifiable graphs. The algorithm that we are going to see here doesn't assume anything. And then we are going to learn a representation of this whole class. But it's still able to do inference for the edges that are learnable later, right? So we cannot learn for every edge what's the causal effect, but for those that we are learned and we are sure that they are unconfounded and they are all this stuff, then we can learn what's the effect of one variable on another. The real effect. Okay. Okay. I'm going to give you the example of this, although I'm almost, I think it's not, I think it's important, so you can play a little bit this week, and then I can revisit the topic. So this separation is a tool that now assumes that you have a Bayesian network. So I tell you that this graph already represents a joint distribution, and then I'm going to be able to list all independencies that are implied or represented in this graph. Okay. Okay. So we know that these graphs are already encoding independencies. There are three types of constructions that I like to just give the names of it, although yeah, it's not completely necessary, but I like the name because it's going to appear all the time. The first one is called fork, because you can see that there is like a separation, right? It's opening two paths from the variable in the middle. So the variable in the middle is a common cause of x and y. This term was created when people created the theory without latent confounding. So the variable in the middle doesn't need to be actually a fork to have this type of to imply these two independencies. But we know that this graph represents these two independencies. So by looking at this graph, I know that's a fork. I know that the variable in the middle, it's a non-collider. Non-collider, it's the opposite of a collider. So everything that's not a collider is a non-collider. So it's a case where Z is not with two arrows heads into it. And that's a case that's going to represent the fact that X and Y are independent of Z and X and Y are dependent. So there is a flow of information. So I like to present these triplets, so we are going to see other, because of the intuition that's behind the paths and the connection, the statistical dependencies. So in this example, I give here that obesity and baldness are correlated marginally. But when you condition on age, they becomes independent. So it's intuitive. Like you see, like people that are both obese and bald, you basically see them happening together. So you see some association, but then you explain this away by conditioning on age. And then you say that, okay, people that are on an older age, they become more obese and maybe more bald. I don't know. Could have sex here to help. Anyways, but there is a way to explain away the dependencies. So there is a flow of information. So the path here between X and Y is open. You're going to start paying attention to this word open. So the path between x and y is open. It's allowing the flow of information from x to y because there is no collision on z. And I'm not doing anything with this z. But once I break the flow by conditioning on z, then there's no more association between x and y. So I'm breaking the flow. So you can think this as like a water pipes. So if I observe a variable or kind of I'm conditioning on a variable, I'm breaking the pipe. So I'm breaking the association. The other one is a mediator. It's again, the pipe is connected. So if this is the true generating model, so a person that has diabetes has a higher chance of getting a stroke, for example, by knowing that it has some family history of diabetes in the family, I know that the person probably has a higher chance of having a stroke. But the influence of the history of his family doesn't matter anymore once I know that the person has diabetes already, right? So it doesn't matter if your father or mother has diabetes if I know if you already have it. So by conditioning on z, x and y become independent. But if I don't know if you have diabetes or not, it still helps to know your family history, right? So, but it's both are equivalent. You just saw these two graphs are equivalent. They're both representing. But the fact here is there's the third one, which is going to represent a different set of independences. And here, what's happened is the following. So suppose that I have diet and physical activity. And the diets that you're having are not physical activity. In my example, it's a simplified example, they are independent, okay? But both affects if the person is obese or not, right? Suppose that I don't know if the person is obese or not. So by just seeing your diet and if you do activity or not, by not knowing, by not looking at you and seeing if you're obese or not, I won't see associations. So not you specifically, but in a population. If I just get like different types of diet and also different levels of activity, these variables are going to appear as independent. I'm assuming that they are independent in the model, so it's not really in reality, but they are independent. But suppose that I know that the person is obese and is doing a lot of exercises. What do you tell me about his diet?
It's gonna be poor or like
Exactly, it's the only explanation. So the fact that I know that the person is obese made the fact that the physical activity is completely associated with diet. So by observing a collider opens the pipe. So it was already blocked. But by observing, maybe I'm removing the knots, like I'm kind of baking the information flow now. It's the same with a descendant of a collider. So never forget about descendants of a collider. They are very important. They are proxy of the collider, basically. So suppose that I don't know that the person is obese. It's the same person. It does a lot of exercises. But I know that it does a lot of exercises, but instead of heart disease, let's say that the person has hypertension or something that tells me about, I think obesity also gives problems with heart disease, but some type of heart disease is that it's also induced by the fact of being obese. Then by proxy, I know that if the person has this disease, it's because it's obese, and by knowing that it's obese and doing a lot of exercise, makes the fact that the chance of the diet being very poor is higher. You understand? So it makes a connection. So descendants of colliders, by being proxy of their own collider, also opens the flow. And
okay, so this is deductive logic you are.
Deductive logic, yes,
Yeah.
because it's functions, right? So if so y is a function of z. Z is a function of x. If I don't know what's z, but I know x, I know that z is a function of x. But once I know the z, I don't need x anymore. It's a function, right? So here I'm using the example. You can put on terms of functions as well. If I know what's the value of so z is a function of x and y. So by knowing the outcome of the function and also one of the arguments, I can predict the other argument. If I know the function of the function, the value of a function of the function, I could also deduct the function itself, and by knowing one argument, I can predict the other. Right? But this, graphically, it's encoded by colliders and non-colliders. So that's two cases here. The cases of non-colliders and the cases of colliders. Allow me to give you just the definition of the separation, then you can... I never know if I should end at 4 or at 4:30, but if you allow me, I will continue. This separation is the following. So you need this idea of activity, which is the one that I just gave. So a triplet is going to be inactive if the variable in the middle is a non-collider and it was observed. So it's always relative to a set Z, right? So remember, I always say I'm observing. So this triplet's open because I observe it's given to. So that is the set Z. So either the variable in the middle is a non-collider and it's in Z. For example, all these cases here. So X and Y are dependent. So see here that I'm using dashed arrows. So the fact that W is a non-collider is the only thing that matters. And it's in square because I'm conditioning on it, right? So W is part of the set Z. So X and Y are independent given a set Z that contains W. Okay? But that's the idea of inactivity. So we are just talking about triplets. So this triplet here becomes inactive once I condition on W. The other case is when it's a collider. So it's here. So it's a triplet where the variable in the middle is a collider, but none of the descendants of the collider, including the collider itself, which is a descendant of itself, it's not on the set Z. So I cannot condition on a set that includes the collider. As long as I'm not doing this triplet is inactive. It's as it is. So in this triplet, X is independent of Y. Not conditioning on anything. Then, so that's the whole scenario of active and inactive triplets. Is exactly what I said before. You can review later. But then we can define the separation. Then the separation is the following. So it's going to be in two parts. The definition is going to be in two parts, and I have to look at every path between two variables. So if I want to see if X is separated from Y, I have to look at every path between X and Y and check the following. Maybe I should go directly to the example. So a path P in an ADMG is disseparated or blocked by a set of variables Z if and only if contains at least one inactive triplet. I just need one. If I have two, it's more than blocked, but I need at least one. So for example, okay, and I could work with sets X and Y, right? So if I'm talking about sets X and Y, I have to check every path between a node in X and every node in a path in Y, right? But let's keep it simple. Suppose that X is just a singleton, right? So just one variable. And the only path between X and Y is this path here. I want to know Z disseparates X and Y, where Z is this set. Okay, so let's start with the empty set. Is X separated from Y, disseparated from Y, given the empty set? I just need one inactive triplet in this path. The first triplet is X, B, and W. It's a non-collider, So the pipes are connected, and Z doesn't contain B. So I'm not observing B, I'm not conditioning on B. So that the information is flow, right? So X, B, and W is active. The second triplet is B, W, and Y, right? The second triplet here. It's the same case. It's a non-collider. B, W, and Y. The W is a non-collider, and W is not part of the set that I'm observing. So B is transferring information to Y freely. So this triplet is also active. So if Z is the empty set, what do you think about the whole path? Is the information from X arriving, reaching Y or not? It is. So this path is open, is not blocked. They are all synonymous. So this path is not open. So if Z separates X and Y, then not. This separation is if we block all paths between every X and every Y. What about the B? If Z contains B now, what changes? What happens with the first triplet? Becomes inactive. So the information from X can reach the Y or not? No. So the whole path is blocked. And since it's the only path, X is separated from Y. What about W? Same thing. What about both? More than necessary. That's the case of a collider, right? So what happens then here? So it's the other case of a triplet. So if the variable in the middle is a collider and I'm not conditioning on the variable itself or any descendant of the collider, is the information from X reaching W? It's the case of the Mount Hall problem. I'm not conditioning on B. B is not part of... sorry, I was talking here. So I'm not conditioning on anything. So this triplet is inactive. Similar with the second. So the empty set makes X and Y disseparated. What about adding B to Z? Now the information from X reads W. But is the information from B reaching Y? Right? So the information is coming here. This is open. So it's coming now here. But what about this? This is
Inactive.
This is inactive. So it stops there. So it doesn't reach Y. So by conditioning on B, it still keeps, it's open one side, but it's not everything. So so I still have one triplet inactive. And by having one triplet inactive, it's sufficient to have my whole path blocked. So this path is blocked and the X is separated from Y. Same for W. What about both?
No longer.
No longer, right?
Yeah.
Okay. So that is this other example. I will give you this for home, if you want. I'm always afraid of going very well. But this one is a bit tricky. Let's see if I see it right now. Let's just go over. I want that X and Y. What about this? So which set disseparates X and Y?
X and Y or X and W?
X and Y. This one
The
here.
last one. Okay.
Because it's the trickier one.
A and Z maybe?
No, Z is a collider. You don't want it in Z. Well, You don't want Z and Z.
Exactly. Perfect. Just A. If you condition on Z, U opens. If you condition on W, also opens. You just need A. Right? So X is dependent of Y given Z. Is dependent of Y given W. And this is represented by D connections, which is the opposite of these separations. So by just looking at the graph, I know everything about the joint probability here. I know that A is independent of Z given X and Y. I know that X is independent of Y just given A, but not given Z, but not given W. I know that Y is independent of W given Z, just this. This is also blocking other paths there. You have to look at all paths, right? So W and Y, that is this path, but there is also this path. Have to be very comprehensive. So this is a lot of information encoded. So it's really useful. So by knowing this, you can even, that's me going far, you can even, I'm just going to show this because it's really nice. I can even define something that's called Markov boundary. I'll revisit this next lecture because it's too much for one lecture. But by looking at this graph, I know all variables that are going to be associated to it if I condition something. So V marginally is dependent of everything that's in gray, right? Once I condition, first I have the neighbors. These are easy, right? So neighbors are like either parents or children, so they are directly connected. So the neighbors are easy. But conditioning on this opens here and makes this variable that's not even, it's nothing. Like if you consider functions, V and this variable should be independent. But the fact that I condition on the child, I created an association. So in our regression, for example, if I condition V to all gray nodes, all of them are going to be significant, even this one. But you never know by a regression which type of association are you creating. If it's like a direct association, it's a cause, if it's like through colliders. And it can be worse. This is the case of when we have bidirected edges. So we can connect by just conditioning on colliders. So this V can be connected, if this can goes very far. Like by conditioning on the neighbor, I make this association with the other, which I mix with the other, and it could be, I mean, now it's no longer an arrowhead here. But I can create again here or there. So by looking on a graph, I know automatically if I condition on a variable, I will have another association or not.
In case of having confounder, we decided if it is collider or not with respect to the first immediate arrow. That's true. For example,
So collider is just by getting two arrowheads into it. This is collider.
For example, this one, exactly this one.
Yes.
Is it collider or not?
It's collider.
Why? There is no arrow to it. We have
Yes.
just this-
So the definition, the original definition of a collider is called common effect. But this is outdated because then they changed the definitions to include confounders. And collider is just a node that has two arrowheads. So collider, first of all, is relative to a path, right? So a variable can be a collider in a path and not a collider in another path, right? So I can have like this. Right, so in this path, B is a collider. In this path, B is not a collider. But this doesn't need to be like this. It could be like this. So the only thing that matters is the arrowhead. In this path, both arrowheads that are incident to B are there, right? In B, are into B. This makes collider. And the non-collider is everything else. So it could be like this is a non-collider, so it could be also this. So this is also non-collider because there's no two arrowheads.
So this dashed arrows is still because we have incoming arrows, it is collider.
Yes, and if you imagine, this is just a simplification of the variable u. So what will happen now is like a, u, actually let's write like this. That's the real graph. You're just simplifying. So there's two collider. And since you don't observe, you cannot condition on this and block the path. So this path here is represented by just one triplet, but is actually open when you condition on B. Right? So it's just a way to visualize. Yeah, but we can revisit this. Try to use I'm so sorry, I'm very slow because I like to talk, but if you're interested, I recommend you to use the fusion, causal fusion, this week to try this separation and play a lot with it. Basically draw your graphs, and there is a tool there where it's going to take a while. There is a tool where you can just check A is independent of B, and then you try all the variables. It's very easy to, if you want to go, you can go, but otherwise I will show here how to do it. That's the best way to learn. Create graphs. Don't forget about the descendants of colliders, because many times the colliders are here. So when you have like this formation, you know, something like this, it's easy to see the descendant of a collider. But if I draw something like this, this is a descendant of this collider. So I don't know, sometimes like reshaping the graph makes it very hard to see that a variable is a descendant of a collider. It's not really, but yeah, I don't know what's happening here.
And that isn't a descendant of a collider, or is it also?
What?
In what you just wrote down, so.
Yeah, E is a descendant of the collider.
And Z?
Z is also a descendant of collider.
Okay, yes.
Yes.
B also.
So the collider is B here.
So
That is.
we said that each node is a collider.
Oh yes. If you condition on the so if you condition on the collider, also opens the path. So many times we say definitions that either conditioning on the collider or on the descendants, but you could simplify by saying by conditioning on descendants of collider, because it includes the variable itself. So I think in the beginning people tried to make the definition not so hard by just saying descendants, but you never know. You can find papers where they just defined it like this. But yes, variable itself or descendants. Right. Yeah, so don't know.
I think you don't have internet.
You don't have internet?
On your laptop I saw that you don't have internet.
It's here.
No, yes.
Oh, it's loading now. I think it was stuck somehow. You are so nice, first thing. Yeah, I have a few graphs. That is this. Can you see it?
Yep.
Yeah, so that is here, this separation. Okay, path analysis, this separation. So I can ask, so you can draw this graph. I can draw later for you, but I draw already. And you can ask, for example, is Z2 and Z3 independent, or actually disseparated? And it's saying not. Can you say why?
The collider Z1.
Z2 and Z3. So that is this path, which has Y as a collider, so it's fine. That is this path, which has a collider, so it's fine. That is this path, which has a collider, but it's fine. But that is this path that has no collider, and it's open. And it's nice because you can ask here, show. That's the path that's open. You can go also here. There's this other path that's open. So there's two paths, it's open. Now, okay, let's try to condition on X. It's still not separated. Can someone tell me why?
Because of the one. No?
Sorry?
It's because of Z1. This path is
Which path?
Z2, Z1, Z3.
Exactly. Why? Because X is a descendant of this collider. So you see how is this tricky? So it shows here that, first of all, there is this. So we are opening the collider by conditioning on the collider itself, and then it's Z1. I mean, you could try to condition on Z1. But there is the other path, which is the one that she told me, which is because X is a descendant of Z1. And if I condition on Z1, now it's doomed, right? So we are conditioning the collider itself. And that's that one that was open, now is closed, but there is still this one. So that's a case where Z2 and Z3 are not connected, but they are not separable. Interesting, right? So there's no set that separates Z2 and Z3 in this graph. So Z2 and Z3 are dependent in the joint distribution for given any set, even the empty set. So it's interesting. So you can draw your graph by just, here's a circle. You can change the grid if you want here. I like to put the grid very small. So you can add the variables. You can have like this thing here. You can click here, it makes things easier to add. So I can add like many graphs, many nodes. This is the directed edge, so I can add edges like this. This is the bidirected edge, so I can add stuff. That's ugly, so I move a little bit. Oops, not, oh, okay.
I have to click very careful, I guess.
Yeah. Okay, so I can move stuff. And then I can ask questions again. So what about Z and that's, if I don't like this, let's change the order so I can move here. So what about Z and W? So they're not because of this path. So I condition on Y. Now it's separated, right? So you can play with your own graph. Actually, I would start soon playing with this because you see that there are a lot of things that we are going to learn later. This is I can clean. But I use this a lot for my research. So even though I learned this for years, I still use it because it's useful. Like you draw a huge graph and then you can automatically see what's the that is this conditional independencies here. So all the independencies that are implied are here, the minimal ones. So W is independent of Z given Y, and X is, what is X? X is independent of Z, right? So those are the so these separations, they imply conditional independencies, right? So those are the implied conditional independencies. So basically all the separations that exist in the graph, they are listed here. They have these colors just to help to show here. But by adding, let's pick another graph like this one, so you have more. So you see I have a lot of graphs for. Then there's no condition independencies implied. I recommend you to use. It's not that hard to intuitively learn. So there's this weird one as well. And maybe if you have questions, we can use sometime next lecture. I can help you also. Yeah, that's the best way to start. So we don't have an exercise sheet this week. I would recommend you to just play with this until Ian is better. Okay. So sorry again for taking a lot. I really like to talk. I don't mind at all. I just don't want to stay, to force you to stay. So I kind of covered everything that I wanted, and I really prefer that we talk and we discuss and you stay, and then you learn during the lecture. Then you go back and wait, I don't know, a few lectures to actually.
So we have a class.
Yeah, sure. Yeah, that's it. Thank you.